The geometric series. The geometric series is the sum of the terms of any geometric sequence. So what is the difference between the geometric sequence and the geometric series? The geometric sequence is the sequence, which is A, the first term, the second term is AR, the third term is AR to the power of 2, and the next term is AR to the power of 3, and the last term L is AR to the power of n minus 1. And geometric series is the sum of all these terms. So the summation of AR, A multiplied by R to the power of I minus 1, and I from 1 to n. So Sn, the sum of all terms of the geometric series is A plus AR plus AR to the power of 2 plus all terms reaching AR to the power of n minus 2 plus AR to the power of n minus 1. Multiply all terms of this equation by R. Multiply all terms of this equation by R. When multiplying it by R, you will get R multiplied by Sn here in the left-hand side, and A multiplied by R multiplied by R, it will be AR, okay? And then AR multiplied by R, it will be AR to the power of 2, and AR to the power of 2 multiplied by R, it will be AR to the power of 3, and multiply all terms by R, and when we went to the last two terms here, AR to the power of n minus 2 multiplied by R. AR to the power of n minus 2 multiplied by R. It's R to the power of 1, and when multiplying like bases, we add powers, so it will be AR to the power of n minus 1. And when multiplying AR to the power of n minus 1 by R, AR to the power of n minus 1 multiplied by R, it's R to the power of 1. It will be AR to the power of n. It will be AR to the power of n. So we have here two equations. The first equation is Sn equals all these terms, and the second equation, it's R multiplied by Sn equals all these terms. What I want from you to focus on the first term here, it's A. And the first term here is AR. Okay? They are not the same. But all terms after A, okay, here, it will be AR, like this term. So AR here is repeated in both of them. And when reaching the last term here, it will be AR to the power of n minus 1. And the last term here is AR to the power of n. So A here, the first term here is A, and A exists in S of n, and it doesn't exist in this equation, in equation 2. And AR to the power of n exists in the second equation and doesn't exist in the first equation. Subtract 2 from 1. So you will end up with Sn minus Rsn equals, when subtracting them, you will get here AR and AR cancel them out, and AR to the power of 2 and AR to the power of 2 cancel them out. And all terms after that, they are going to be cancelled. And AR to the power of n minus 2, and here we have AR to the power of n minus 2. And here it's AR to the power of n minus 1. Okay, and here we have AR to the power of n minus 1. Cancel them out. You are left with A here minus AR to the power of n. We can take Sn here as a factor. Then here we have in the brackets 1 minus R. And here we can take A as a factor. Then you will get 1 minus R to the power of n. So to get the value of Sn, divide both sides by 1 minus R here, and divided by 1 minus R here. So Sn equals A multiplied by 1 minus R to the power of n over 1 minus R. That's the sum of all terms, that's the sum of all terms of a geometric sequence, Sn. So Sn equals A multiplied by 1 minus R to the power of N over 1 minus R. You know, we can switch of 1 minus R to the power of N. We can multiply by -1 here and -1 here. If you multiply 1 minus R to the power of N by -1 and here 1 minus R. If you multiply it by -1 at the top and -1 at the bottom, you will get at the end, it's R to the power of N minus 1 and here minus 1. So we can say that Sn equals also A multiplied by R to the power of N minus 1 over R minus 1. They are the same. Both of them are the same. There is no difference between them. So Sn equals A multiplied by 1. If you started by 1 here at the top, so start by 1 at the bottom. So it's A multiplied by 1 minus R to the power of N over 1 minus R, or R to the power of N here minus 1 and R minus 1 here at the bottom. Okay. What if we expanded A multiplied by A to the power of N? So it will be A R to the power of N minus A. I expanded here over R minus 1. You know that the last term is A multiplied by R raised to the power of N minus 1. Multiply both sides by R. So LR equals A multiplied by R to the power of N minus 1 multiplied by R to the power of 1. When multiplying like bases, we add powers. So it will be LR equals A R to the power of N. That's A. So LR equals AR to the power of N. And here we have AR to the power of N. So we can substitute, instead of AR to the power of N, we can write LR. We will write LR. So it's LR minus A over R minus 1. So we have two rules to find the sum of a geometric series. Sn equals A multiplied by 1 minus R to the power of N over 1 minus R, or we can say it's LR minus A over R minus 1. It's LR minus A over R minus 1. And we can write this rule as it's A minus LR over 1 minus R. That's it. You know that S4 means the sum of the first 4 terms. It's T1 plus T2 plus T3 plus T4. And S3 means the sum of the first 3 terms. It's T1 plus T2 plus T3. If you subtract T4 minus T3, you will get here T4. So S4 minus S3 equals T3. And if I ask you about S5 minus S4 equals T5, and S13 minus S12 equals T12. What about geometric series? Specifically, infinite geometric series. The meaning of infinite has no end. So there is no last term. Like this sequence, 4, 2, 1, half, 1 over 4, 1 over 8, 1 over 16. Okay, it has no end. This is infinite geometric series. Infinite geometric sequence has no end. Unlike this sequence, it's 5, 10, 20, 40, 80, 160, and so on. We have 2 types of infinite geometric series. Convergent. The convergent can be summed. We can find the sum of this series. It's called convergent. And here, the second type is divergent. The divergent series has no sum. We couldn't add all these terms of the sequence, so has no sum. Here in this series or in this sequence, R is half, and R, the common ratio is less than 1, the absolute value of R less than 1. That means R is greater than -1 and less than half. Can be summed. We can find the sum of this geometric series. And here R equals 2. So absolute value of R is greater than 1. When R greater than 1 or R less than -1, the geometric series has no sum, or we couldn't add all these terms. And you know that Sn equals A multiplied by R to the power of n minus 1 over R minus 1. Or we can write Sn equals A multiplied minus 1 minus R to the power of n over R minus 1. You know, if absolute value of R is less than 1, that means R is greater than -1 and less than 1, like half, for instance. If we want to find the sum of an infinite number of terms, so n here in this case, n approaches to positive infinity. So half raised to the power of infinity. When we raise half to the power infinity, you will get 0. When we raise any number between -1 and 1 to the power of infinity, you will get 0. And if you want to check it, just write on the calculator half to the power of, let's say, 1000. You will get a value close to 0, 0.00. So R to the power of n in this case equals 0 or approaches 0. So Sn equals A multiplied by 1 minus 0 over R over 1 minus R. Here it's 1 minus R. 1 minus 1. So multiply, it will be A at the top, and at the bottom it's 1 minus R. So S infinity equals A over 1 minus R. Which of the following can be summed up to infinity? Then find the sum, if possible. Number 1. Here is the geometric series, and the geometric sequence 67, 21, 63, and so on. So or in this case, it's a 21 over 7 equal 3. And absolute value of R in this case is greater than 1. So here, this series cannot be summed. In the second one, it's 75. Then here, after 75, it's 45 and 27. The geometric sequence 75, 45, 27, and so on. And the geometric series is the sum of all these terms. So here R is 45 divided by 75 equals 3 over 5. And because absolute value of R in this case is less than 1, so this series can be summed up to infinity. And to find the sum S infinity here in this case, it's A over 1 minus R. And A here is 75 over 1 minus R3 over 5. By using the calculator, you will get 187.5. That's it. Here we have a recurring decimal 0.3 recurring, and what I want to change it into a common fraction. What does it mean? Let's analyze it. Do you know 0.3 recurring means 0.3333 and so on? has no end, 3 is repeated. So here we can write this recurring decimal as 0.3 plus 0.03 plus 0.003. So it's a geometric series now. And the geometric series came from the geometric sequence 0.3, then 0.03, then 0.003, and so on. You know, or in this case, it's 0.03 divided by 0.3. Okay, multiply by 100 at the top, and at the bottom it will be 3 over, multiply by 100, it will be 30, it will be 0.1. So R in this case is 0.1. R in this case is 0.1. That's all. Okay. And A, the first term is 0.3. So I want to get the sum. So Sn here in this case, S infinity equals A over 1 minus R. What is A in this case? A is 0.3 over 1 minus 0.1. Okay, by using the calculator, you will get to 1 over 3. That's it. Here in this question, we have 0.18 recurring. I wanna write it as a fraction. So 0.18 recurring decimal, it's 0.18181818, okay, till infinity. And this decimal is repeated 1, then 8, 1, then 8, 1, then 8. So we can write it as 0.18 plus 0.0018 plus 0.000018, and so on. And this is a geometric series. And this geometric series came from geometric sequence. And the geometric sequence in this case, it's 0.18, then 0.0018, then 0.004018, and so on. R here in this case will be 0.0018 divided by 0.18, which is 0.01. That's all. Because R is less than 1, absolute value of R is less than 1. So we can find the sum of this series. The sum is A over 1 minus R. What is A here? It's 0.18 over 1 minus R. It's 1 minus R is 0.01. By using the calculator, you will get 2 over 11. That's the common fraction, or the fraction of this recurring decimal. Prove that the sequence Dn equals 10 multiplied by 2 to the power of n minus 2 is a geometric sequence. Then find the number of terms must be taken from the sequence starting from the first term, such that their sum is 2,555. How can we prove that the sequence is a geometric sequence? Divide Tn plus 1 divided by Tn. So Tn plus 1, it's 10 multiplied by 2 to the power of, instead of n here, write n plus 1. So pay attention, it's n plus 1, and here we have minus 2. Over Tn, which is 10 multiplied by 2 to the power of n minus 2. So it will be 10 times 2 to the power of n, and 1 minus 2, it's minus 1. Over 10 times 2 to the power of n minus 2. Cancel 10 and 10. So you will end up with n 2 to the power of n minus 1 minus n plus 2. Cancel them out. So it will be 2 here, 2 to the power of 1. So we have a constant number, which is r. So r here equals 2. Because r equals 2, we have got a constant number. So the sequence is a geometric sequence. How can we find the number of times n to get a sum of 2,555? You know, Tn equals a multiplied by 1 minus r to the power of n over 1 minus r. That's, sorry, Sn. Sn here. Instead of Sn, we are going to write 2,555 equals a. A in this sequence, how can we get a? And instead of n, write 1. So find T1. T1 equals 10 times 2 to the power of 1 minus 2. So T1 equals 10 times 2 to the power of negative 1. So equals 10 times half, which is 5. That's T1. T1, which is A. So here A is 5 multiplied by 1 minus r. R is 2 to the power of n. I don't know what is n. Over 1 minus r, which is 1 minus 2. 1 minus 2 is negative 1. So right here, 2,555 equals 5 times 1, or we can leave 5 now, and here we have 1 minus 2 to the power of n over minus 1. Do cross multiplying. So it will be negative 2,555 equals 5 multiplied by 1 minus 2 to the power of n. Divided by 5 both sides. So it will be, when dividing by 5, 512. So 1 minus 2 to the power of n equals negative 11. We can move it to the next side and this to the next side here. So 2 to the power of n equals 1 plus 511. So 2 to the power of n equals 512. And 512 is 2 to the power of 9. So 2 to the power of n equals 2 to the power of 9. In this case, n equals 9. That's it. Here in this example, Tn is a geometric sequence whose terms are positive. T2 equals T2 equals 6 and T3 minus T1 equals 9. Find the sequence and the sum of the first 12 terms. Here in this case, T2 equals 6. That means AR equals 6. Okay. And T3 minus T1. T3 minus T1 equals 9. And T3 is AR to the power of 2 minus T1 is A equals 9. So in this case, we can take A as a factor. You are left with R to the power of 2 minus 1 equals 9. That is the second equation. Okay. So here we can divide the first equation by the second equation. So A multiplied by R to the power of 2 minus 1 over AR, okay, equals here 9 over 6. Cancel A and A. So you are left with R to the power of 2 minus 1 over R equals 9 over 6, 3 over 2. Do cross multiplying. So 2R to the power of 2 minus 2 equals 3R. Move 3R to the next side. So 2R to the power of 2 minus 3R minus 2 equals 0. Then factorize this expression. It will be 2R plus 1 multiplied by R minus 2 equals 0. Then we have two solutions. The first one, 2R equals negative 1 and R equals 2. R equals negative half is refused here because All terms are positive, so this one is refused. Then R equals 2. How can we get A? Substitute in this equation 1, AR equals 6, and R is 2. So A multiplied by 2 equals 6, 2A equals 6 divided by 2. So A equals 3. A equals 3. How can we get the sequence? Because we have A and R, so the sequence is going to be 3 multiplied by 2, 6 multiplied by 2, 12 multiplied by 2, 24, and so on. That's the sequence. How can we find the sum of all terms of the geometric sequence? Here, the sum Sn equals, as you know, it's A multiplied by 1 minus R to the power of N over 1 minus R. Because we don't have much room here, we are going to write here in this area. So S12, I want to get S12. So S12, it's A, 3 multiplied by 1 minus R to the power of N, 2 to the power of 12 over 1 minus 2 equals 12,285. That's it. I hope you enjoyed this session. See you in the coming episodes. Goodbye.